yeah, so what I want to present today is partly a conceptual vision, partly a little presentation of some older data of mine, and probably mostly you could think of it as like a project proposal of where I want to go from here. So the talk is going to be a bit involved. So I'm going to do something a bit unusual and start with the conclusions. And I'm also going to end with the conclusions. And my hope is that what I say in between will make some sense. But I don't want to get lost along the way. So the conclusions of the talk are that the trophic ecology of flowers and florivores is the foundation of pollination ecology. Secondly, that floral resource limitation and therefore pollinator competition are contingent on floral resource structure. Floral resource structure in turn consists of the dimensions of time, space, and functional traits. These dimensions of floral resource variation are, at least in principle, amenable to measurement and modeling, and ultimately integration with coexistence theory. I'm going to present a demonstration of that later in the talk. For starters, though, I want to take you back 3 years ago. So this is where the last time I did fieldwork, in fact, it was here. So this is pre-pandemic Philadelphia. This is my study system. And it's also my hometown. So this is a place that's very near and dear to my heart. These are my study sites. I had these experimental apiaries set up with a collaborating beekeeper around the city. And from these apiaries, I collected pollen samples. And then I also used these data logging hive scales to monitor colony weight. And the idea was to get this portrait of floral resource usage by honeybees in this complex urban landscape that you could never do traditional floral surveying of. And this is what we found. I'm not going to go too deep into this. If you're interested, the paper is there. But this is these curves here show the weight change of these colonies through time. These are the 2 years of the study. So they're differenced. So when the curve is below 0, the colonies are losing weight. When it's above 0, the colonies are gaining weight. And what I want you to take away from this is simply that the availability of floral resources in the environment as measured by the weight gain of these colonies is extremely dynamic. And there are strong periods of resource availability, of the flux of resources into the colonies, and then periods of resource scarcity where the colonies are losing weight. And at the same time, we can look at the pollen content of the samples throughout this time and see that there's this fluctuating mosaic of taxonomic contribution, of taxonomic composition here too. And as I reflected on this, it just got me thinking about how dynamic floral resources are when they're studied at the landscape scale. I mean, it's one thing to consider individual flowers or even individual study plots. When you start to work at the scale at which pollinators actually interact with the landscape, what emerges is an extremely dynamic, complex picture of the floral resources on which pollinators subsist. Oh, and also I should say that these varied spatially too. So the different taxonomic components, the different flower species that I found, didn't all show up to the same degree at the different sites in the city. So there are certain parts of the city that were dominated by things like Mellolotus. Other parts were dominated by things like Trifolium or Parthenocissus. So that's not yet another dimension of variability in this system. And I'm going to reproduce a back of the napkin diagram that I made at one point when I was reflecting on this that has become more sophisticated. But basically, you can describe this variation spatially in terms of the northing and easting. So just as an XY system here. And then for any point there, you can describe the variation in time. So I'm thinking of your seasonal time here, and you get a curve such as the ones I just showed you. And then at any point in that temporal time series, you can take a slice of it and you have a matrix of taxonomic composition. And all of these dimensions of the floral resource environment vary simultaneously. And it is that joint variation that creates the floral resource topography, so to speak, with which florivores, in this case honeybees, interact, on which they subsist. And what I'm going to make the case for is ultimately is this structure that determines whether and to what extent they would compete for floral resources. But hold that thought. The outline here, so that was the prelude. The structure of the rest of the talk is I want to explore the basic biology of flowers as food. I think this is the fundamental trophic ecology of floral resources. We're going to explore why getting eaten can be a good thing. Then 50 years of equivocity, we're going to do a quick review of pollinator competition. And then I want to bring these two things into conversation around the issue of floral resource limitation to try to use the concept of floral resource limitation to reconcile the trophic ecology of floral resources with the concept of pollinator competition. We will explore floral resource competition in terms of floral resource structure, as I've hinted at. I made an R package, and you can tell it's really official because I made a hex sticker to go with it. So it's basically on par with dplyr now. Not really, of course, but I hope that you'll find it useful. And then I want to present a research agenda to follow up on these ideas, both empirically and theoretically. Okay, so flowers as food. This is where it all starts for me. This is honestly where I find the most, this is the part of the story that I find the most interesting and the most uncharted, so to speak. There's a lot of room for discovery here, but I want to start with this quote from a great paper by Jeff Allerton. I'm going to break the rules of presentations and read you a chunk of text because it is good. So Jeff Allerton writes, the first appearance of flowering plants set the scene for one of the iconic stories of evolutionary biology in which supposedly primitive wind pollination by gymnosperms was replaced by ever more complex animal pollination in flowering plants, leading to the diversification and dominance of angiosperms. Does that story sound familiar to anybody? Have you told that story before? Well, what Jeff says next is that it is a story that has been repeated in many textbooks and documentaries, even up to recent times. The problem is that it is incorrect. What's wrong with that story, Jeff? Well, to finish answering that question, we'll turn to another of my favorite papers by Dawn Frame. She notes that for the purposes of our discussion, it is evident that, for example, the Gymnospermous female strobili are homologous to Angiospermous inflorescences, and that gymnosperms bear flowers just as angiosperms do. And this is the same point that Jeff Allerton makes, is that this is a gymnosperm here. You may not have guessed this. This is from the order Nitales. This is a flower. I don't care if angiosperms are called flowering plants. This is a gymnosperm and it has a flower. And this is something we have to accept. Flowers preceded angiosperms. And the world in which angiosperms arose was one in which flowers already existed, and indeed relationships between flowers and insects already existed. But what made the difference is not that angiosperms invented flowers, but that they invented edibility, so to speak. What Frame writes is that what differentiates most angiosperms is their edibility, and this extends to their flower. Angiosperms, more than any plant lineage that preceded them, succeeded in harnessing the basically negative phenomenon of herbivory into florivory. They focused herbivory on the flower and harnessed that into pollination. And the result is that angiosperms took over the world. This is a time series going back to the Jurassic, and basically what it shows is just this dramatic transition. So this represents plant-associated insect families. This is like basically the degree to which insects interact with plants. And essentially what we see is there was a time when insects interacted with gymnosperms. Once angiosperms entered the scene, though, they were just so much better to eat that insects shifted entirely. And this includes not just interactions with flowers, but that is perhaps the most dramatic of these. And so today we now have 369,000 angiosperms, 352,000 species of flower visiting arthropods. Does that number surprise anybody? And together, this is a third of all described extant eukaryotic biodiversity is either a flowering plant or a flower visiting insect. That's pretty dramatic, right? And yet you don't hear this talked about in the trophic ecology literature. The trophic interface between flowers and florivores, while it is clearly a foundation of global biodiversity, has been almost completely eclipsed in the trophic ecology literature by other forms of herbivory, particularly folivory, the consumption of leaves. Yet, meanwhile, pollination ecology has risen to the forefront of ecology. It's one of the most prolific subdisciplines of ecology. All the while, though, it has been overlooked that the underpinnings of pollination ecology are this trophic ecology of flowers and florivores. And one particular case where this really comes to the forefront is in the problem of pollinator competition. This is a picture I took from right outside our building here. This is Bombus pascorum on the bottom and Bombus silvarum, I think, on top here. They are sharing a thistle. This was in September or something, was starting to get chilly. I think this is probably some of the last nectar that they found this year, unfortunately. But the study of pollinator competition is not new. It actually started in the 70s. At that time, this was the golden age of classical niche theories. This is when people like Hutchinson and MacArthur were extremely influential. And what everybody wanted to do was find some way to map empirical systems onto these notions of niche overlap and limiting similarity and things like that. And so this is exemplified in the case of pollinator competition by this classic paper from David Inouye. And basically what he's showing here is that, can you see my pointer when I move it around? Good. These are bumblebee tongue lengths and in these two communities. And you see that bumblebee tongue lengths are dispersed. There's trait dispersion, which he interprets as limiting similarity. And you say, oh, wait, these two are really close together. And then he points out, no, Bombus occidentalis is a robber, so that doesn't count. And he says, okay, you can have three species, a short, a medium, and a long-tongued, and a robber. And any more than that, and they compete too much and will be excluded. This was beautiful. He even recovers the ratio that Hutchinson suggested should control the degree of similarity between the traits of coexisting species. The only problem with all this is it didn't really work when you extended it outside of the system in which it was formulated. So if you go to Europe, you look at the work from Ranta and Vepselainen, it looks rather different, doesn't it? All the bumblebees are clustered with very, very similar tongue lengths, and there's like 12 different species coexisting. And that's what you find again and again when you study bumblebees in Europe. And it's also what Paul Williams found. He had like 14 species that were all existing in one plot in Dungeness in the UK. And so clearly the kind of the elegant theory of limiting similarity kind of fell apart for describing pollinator competition. And then competition theory itself fell apart. I'm going to read you another block of text just because I love Daniel Simberloff's way with words. He says, current ecological theory on present effects of interspecific competition, as summarized by Roughgarden, has not helped us to understand how nature works. It has generated predictions that are either practically untestable by virtue of unmeasurable parameters or unrealizable assumptions, or trivially true. Does it sound like any research you've experienced? Whether or not it has influenced a productive set of investigators of natural systems is debatable, but such influences are not explicit in the writings of most such investigators. On the other hand, the theory has caused a generation of ecologists to waste a monumental amount of time. However, and I'll just point out that he's not going to qualify the statement he just made. He's just going to go on to make it further. So classic competition theory collapsed in the 1980s, in part because of an overconfidence in mathematical simplifications. And it frankly became kind of embarrassing to talk about niche and competition until the late 90s or early 2000s when Jonathan Chase and others kind of resurrected the niche concept and brought it into the 21st century with a degree of respectability. So you can talk about niche and competition now, but for a while you couldn't. And so the question of pollinator competition became something very empirical and applied, because it was still an issue, but it was not cool anymore to address it with theory. So you just went out and measured things and hoped that it would all make sense. And what motivated this, though, was the concern about competition between honeybees and wild pollinators, which until then had not been a concern. Back in the theoretical age, the fact that bumblebees were bees and in fact pollinators was kind of incidental to the fact that they had tongues that could be measured, because all that mattered was the instantiation of the theory. But now the concern is, are honeybees competing with wild pollinators? Ingolf was actually involved in some of the early work here in his 2000 paper, and that was at the beginning of this explosion of empirical work. And this is from Rachel Mallinger's work in her review, a meta-analysis of 2017. But I think it's safe to say this curve has not leveled off. In the years that have followed, the expansion of empirical measures of competition between pollinators has increased exponentially. The problem is the interpretation has been anything but clear. So this is, again, from the Mallinger paper. And we see that the effect of managed bees on wild pollinators is neutral or mixed about as often as it is negative. And so you're left saying, I don't quite know what to make of this. And you kind of get the impression in a lot of these studies that there's such a rush to measure things that we're not quite sure what we're measuring or what to make of it in the end. I think it's safe to say we've all been in that situation too. And this is often what happens when you have a proliferation of empiricism without a reference to theory to guide its interpretation. Then most recently, though, since about 2018, I would say, we've entered an age that I'm calling pollinator polemics, where this has spilled into the popular media and just to the general discussion, where people are actually mad about this. This has become a contentious issue. And there's especially a lot of shade being thrown on honeybees and sometimes on honeybee researchers. And regrettably, the tone of this sometimes becomes rather cantankerous. What's missing in all of this? We've been through theory, we've been through empiricism, now we're into just arguing with each other. What I want to point out is that at no point in this process from the 1970s until today has any real attention been given to the floral resources that pollinators are presumed to be competing for. And again, my thesis here is that the trophic ecology of flowers and floravores is the foundation of pollination ecology. And if there is a logic to the competition between pollinators, it is going to be found in the floral resources for which they compete, as much as it's going to be found in something like the tongue length of individual pollinators. I think the place to start here is to ask a very basic question that for some reason has gone almost entirely unasked in the 50 years of talking about pollinator competition. And that is, are floral resources limiting? Have you ever thought about this question? It's come up in conversation a couple times, I think. I know we've thought about it in Berchtesgaden with our bumblebee system. Is there a reason to expect bumblebees to be competing in that system? Or are there just so many flowers and such a short growing season that something else entirely is limiting these populations? Well, to guide our discussion, I want to introduce you to some deceased ecologists. Okay, Malthus doesn't count as an ecologist, but we're still gonna hear from him. So Thomas Malthus really should be considered probably the father of ecology, even though he never used the word and was himself an economist. But it was really, he inspired Darwin to Darwin's notion of differential survival and therefore natural selection. And the gist of what you need to get from Malthus is that this is a quote from his famous essay on population. He says, population, when unchecked, increases in a geometrical ratio. Subsistence increases in only an arithmetical ratio. And this is just the idea that populations will always tend to outstrip their resources and crash in the absence of other controls on population growth. And this was axiomatic in first evolutionary and then ecological thought. This is the basis of things like Lotka Volterra. The next revolutionary thing that was said, though, it was 160 years later by this is famous paper, the HSS paper by Harrison, Smith, and Slobodkin, where they proposed that the herbivores, in contrast to predators and detritivores, are seldom food limited and appear most often to be predator limited, and therefore are not likely to compete for common resources. And this introduced the whole possibility that systems can be top-down regulated and therefore not resource limited. And so I like how in this picture it kind of looks like Neil Hairston is leaning over to whisper something to Thomas Malthus. They were an argumentative bunch too, so that would not be an unrealistic scenario. The question, though, is where do pollinators fit in this? Which side of this divide do pollinators belong to? And we can start with a somewhat trivial but important observation that florivory is a special case of herbivory. Pollinators are herbivores, and so to the extent that the green world hypothesis, as it is called, is deemed an accurate account of herbivores and plants in general, it should enjoy a priori plausibility as an account of florivores and flowers, right? Moreover, also kind of at a theoretical level, nectar and pollen are weakly defended relative to foliage. And one of the arguments against the green world hypothesis is that plant defenses render a lot of the greenery of the world inedible. But nectar and pollen they're not completely undefended, but they're weakly defended. And that's because obviously intoxicating your pollinators has a negative effect on fitness in general. However, there's also theoretical merit to supposing Malthusian conditions prevail among pollinators and flowers. And there's this very interesting paper that just came out this year from Francis Ratnieks and Nicholas Balfour. And what they point out is that, what they propose is that when floral resources are limiting, that is, in this case, when nectar specifically is scarce, flowers should be receiving saturating visitation, right? If pollinators are searching for a scarce resource, there should be no shortage of pollination visits to flowers. And the ironic effect there is that that's actually going to relax selection pressure in plants for the production of nectar, and it's going to drive nectar production even lower, and it's going to create this kind of spiral of nectar scarcity that's going to push the system toward ever more Malthusian states. Importantly, though, that works both ways. When pollinator visitation is limiting, and therefore nectar is super abundant, that's going to force plants to compete with each other, and it's going to drive the system toward ever more sweet world conditions, so to speak, where nectar is super abundant and non-limiting, and pollinators do not compete. This, in fact, was demonstrated empirically, and it seems that Ratnieks and Balfour missed this. So in 2014, 7 years ago, Junpeng Mu, I worked with him actually at Penn State. This is work he did in China, though. And he demonstrated this in the Tibetan lotus. This was shown that if you expose this flower to high densities of honeybees, it over generational time evolutionarily reduces nectar production, which is just a really groundbreaking finding. And then another consideration here is that apiculture really breaks all rules of species coexistence and limitation, because the honeybees, where they are stocked, and especially in commercial apiculture, they are stocked completely irrespective of the carrying capacity, so to speak, of the landscape. And so moreover, they're stocked irrespective of any control of population. They're simply stocked to the degree that the beekeeper chooses to stock them. Then if we try to sort this out with the empirical literature, again, it's really so equivocal that you're left kind of throwing up your hands and saying, I can't make a categorical answer to this question. And I think what this means is that we need to abandon the categorical question and instead ask questions of ecological contingency. Instead of asking, are resources limiting, we need to ask, where are they limiting? When are they limiting? And in what functional compartments are they limiting? And so after a certain amount of labor, I found a way to alliterate all this. We can have Malthusian mosaics in space. We can have Malthusian moments in time, and Malthusian modules in our network. I hope that you get as much satisfaction out of the alliteration as I did. Anyway, the idea here is that resource limitation and therefore competition are ecologically contingent. And the question is, where does limitation and competition occur? When does it occur? And what functional compartments does it occur? And importantly, what causes these states and what causes transitions between them? These are the kinds of questions we need to answer. And I think the way to answer these is to attend closely to the structure of floral resources. And for this, I'm going to throw out the back of the napkin drawing here and provide a more a polished illustration. So my argument is that floral resource structure essentially has three sets of dimensions, so to speak, that we have to consider. One is time. Time can be seasonal. It can also be within a day. It can be DL time. These changes in time are distributed in space, and therefore we need to consider it for a given spatially defined location and account for the spatial heterogeneity that emerges. And then all of these dimensions of variation are effectively compartmentalized by the floral traits that determine which pollinators interact with which plants. I'm going to zoom in on these now. Just check the time. Yeah, we're doing okay. So in terms of time, we can look at seasonal time, and the best illustration of this comes from a recent paper by Tom Timberlake. It's really an excellent paper I encourage you to look at. But this was a study of bumblebees and floral resources in farmlands in the UK, and he found that this red line represents the resource requirements of a bumblebee population, and the black line represents the nectar available in the landscape. And you can see that there are these discrete periods where resources are scarce and other periods where they seem to superabound. Time, however, can also vary within a day, DL time. And I don't have as nice a figure to illustrate this, but I want to point out an interesting paper that you probably haven't seen. It's kind of an old one and kind of an applied one, but it turns out to be very relevant here. This shows the foraging activity of 3 bee species in pumpkins. This is Pollinator pruinosa, which is a squash specialist, a cucurbit specialist. This is Apis mellifera and Agapostemon. This is so Apis mellifera. These are honeybees. Agapostemon is a genus of sweat bees. And the important thing here is that Pollinator pruinosa gets up so much earlier than honeybees that by the time honeybees are foraging, actually all the pollination has been done. The pollination needs of the plants are saturated before honeybees even make it to the field. And what this means is that it doesn't matter how many honeybees are in the landscape, Pollinator pruinosa is not going to experience competition from them, probably because their foraging happens so much earlier in the day. I'm not saying that's true of systems in general, but it's an illustration of how daily time can matter. Space, I think, is rather more complicated. I'm not gonna say much about it except to point out that I think the key thing here is understanding the different spatial scales with which pollinators interact with the landscape, and this recalls some of Ingolf's work from the early 2000s, in this case with bumblebees. But I'll leave it at that for now. And then in terms of the functional traits of the floral community, in the sort of the popular telling of stories about flowers and pollinators, what is emphasized is the coevolution of fittedness between flowers and pollinators, because the flowers need the pollinators need the flowers, and isn't it beautiful how they all just match perfectly? And there's some truth to that, but it's really rather more complicated because plants don't want everything to visit them, right? They want pollinators that are going to reliably deposit the pollen of the same species and without doing significant damage to the flower or robbing floral resources and such. And so floral traits interact with pollinators with these kind of this dialectic of attraction and repulsion. So they're with like floral scents, volatiles, and colors. Access and preclusion, you see this with the depth of floral corollas. Some pollinators are physically precluded from flowers by the shape of the flower. And reward and penalization. There are floral rewards, and then there are also secondary compounds that effectively protect floral resources from unwanted pollinators. And so it's the interaction of these things that determines the modularity of networks, which has been well demonstrated in the empirical literature. And the idea here is if we want to understand resource limitation and pollinator competition, it may very well be that some of these modules of the network are limiting and others are not, because of the way that the pollinator community is filtered by the floral traits of the plant community. All these dimensions vary simultaneously, and all of them matter. This is what I'm calling the jump to floral hyperspace. This recalls something like Hutchinson's n-dimensional hypervolume, right? And it's at this point that you realize why the theoreticians of the 1970s didn't want to deal with this. This is every theoretician's nightmare. It's just too complex. And it's also why it doesn't come up very much in the empirical literature, because no one's quite sure what to say about it. It's just too much variation all happening at the same time. But my contention here is that it is time to just square up to this complexity and make this complexity itself the subject of our study. And that in doing so, we will clarify things with respect to the theory and also the interpretation of the empirical literature. And as daunting as this seems, this wild fluctuating mosaic in space and time and compartments, I think it actually is tractable, but we need to take it a little bit at a time. So as a demonstration that all hope is not lost, I want to introduce a little R package that I made. It is rudimentary. Please don't judge me by the standards of Hadley Wickham, but it's a start. And I hope that you might find it helpful if you end up doing this kind of work. I find it helpful. And the reason is that I find when I'm dealing with complexity like this, I can't keep it all in my head at the same time. I need a sandbox to play in, so to speak. I need to be able to simulate it. I need knobs that I can turn and see what the results are. And so after thinking about this for a while, I decided to implement it as an R package that is available on GitHub. You can try to break it. It'll probably break eventually, but it should work at least at first. And what it lets you do is first generate a hypothetical landscape. So you feed it the desired patch size and the patch number, which basically controls the grain size. And it'll create a landscape for you with, right now it's hard coded to be 3 different classes, but this part is randomized. So you can look at a landscape and immediately give yourself, your imagination, something to work with, right? Then you can sort of populate it, so to speak, with plants. You can plant your flowers in this landscape, and what it does is it maps flower species to the patch classes that you declared here. And you can do this probabilistically. So you can feed a vector of probabilities, and you can say if patch class equals 0, then it gets assigned one of species 1, 2, and 3 at a probability of 0.25, 0.25. and 0.5. And then you can then randomly populate your landscape with a fixed proportional abundance of these species. And so you can kind of approximate what a real landscape would look like. So here we have our landscape. It's been planted with plants now. Then we need a floral trait table, and we have a really cool one from Matilda Bauda et al. This is a paper you've probably seen. It was a pretty famous one, but it has this beautiful trait table that's buried in the supplemental materials. And you could generate these traits from your own field data, but if you don't have that, you can use these. And what you at least need at minimum is first bloom, peak bloom, and last bloom for all the flowers that you're gonna model. And you need peak floral density and floral concentration per flower. And you can just put all those together arithmetically, and you can determine the total amount of sugar in the landscape at any given time or place. I've implemented this with sugar, so nectar sugar in mind right now, because it's a lot simpler to quantify than pollen. But theoretically, if you have a way of quantifying pollen, you could do the same thing. So I want to break down a little bit how this works. You can aggregate through time, so you can just smush this whole landscape into a time series and say, okay, this is what the overall pattern of floral resource availability looks like in this landscape. And then this should be reminiscent of the kinds of curves that I showed you earlier from my own work and from Tom Timberlake's work. But you can also look at this functional compartmentalization that I mentioned, and you can parse that total floral availability by some kind of categorical floral trait. So in this case, in the Bauda data set, they include Hermann Müller's morphotypology, which describes flowers as being bee flowers, hidden flowers, open flowers, or partly hidden flowers. I don't know how useful that particular typology is, but you can insert whatever one you have handy. And you can see how floral resource availability varies when it is divided across these compartments. And then for the prettiest pictures, you can also just embrace the spatial complexity here. And you can map the sugar availability through time for each patch of your landscape. And so I've pulled out slices of time here on a monthly interval to illustrate this. So I do not get to within day time. I've not implemented that yet, but in principle, I think it can be done. The point here is not to give you answers to the question, but to provide an environment in which you can start to play with things and say, what happens if I did this? What would happen to floral availability if, for example, we went from 50% oilseed rape in a forest meadow oilseed rape landscape to 80%. We can implement this in this model and see what is the effect on floral resource abundance. And if we look at it in aggregate, we see with our 50% oilseed rape treatment, we have these two kind of roughly equal peaks of floral resource availability in spring and summer. And then the effect of intensifying the landscape. So this is a realistic landscape conversion scenario here that's happened all across Europe. The effect of that intensification is an increase of the spring peak, which is driven by the flowering of the oilseed rape, and a pretty dramatic suppression of that summer floral resource peak. And here you can start to reason that the effect of this change would be to intensify competition, if it exists, in summer and to mitigate it in the spring. This at least starts to give us some traction, right? And then we can also parse it by traits, and we can see that what we are increasing when we expand oilseed rape is this one particular flower morphotype, and we are effectively suppressing other flower morphotypes at that same time. So yeah, this is an environment in which to test ideas. If you want to download it, as I said, it currently works. It's on GitHub. If you have questions, you can talk to me about it. This is the last part of the talk, and we're almost done, so I guess the timing is about right. But I want to present what is now, at this point, a vision that is probably going to take the form of some of the work that is done in the Safeguard project, which will be starting next year. I could also imagine it being a DFG grant, so if you have input on this, I would really appreciate your feedback, because we're at the prospective part of the talk now. So first of all, in terms of techniques and applications, this is the empirical sphere of development on this topic. I think we need to develop ways of summarizing this n-dimensional complexity of floral resource structure into some tractable metrics. And so, for example, we might be interested in how low the lowest trough is in the seasonal time series, or what the variance is between the highest and what the variance of resource availability is through seasonal time. These are things that could be extracted. We may be interested in some kind of metric of the configuration of landscape, the spatial configuration of resource availability in the landscape. The idea, though, is to go beyond something like floral richness as the explanatory variable that we use to then predict things about the pollinator community. I think we can do the types of field studies that we're used to, but instead of using floral richness or something, or in addition to using floral richness, we can extract these structural metrics and see if they perhaps explain things about the pollinator community that we could not explain with simpler approaches to floral resources. Secondly, I would love to explore remote sensing techniques for large-scale floral surveying. A lot of these questions that we are asking are inevitably asked at the landscape scale, at scales that we simply can't go out and do quadrat sampling. And I think we are approaching the point where we could estimate floral resource productivity adequately using remote sensing techniques, but I do not personally have that capability. So I'd be interested in talking with those of you who might have more expertise with that. And then I think we can ask some exploratory questions about the impacts of climate and land use change on how they distort floral resource structure. And so just as an example of this, which really I find quite striking, this paper from Caradana et al. And they show that if we look at the seasonal curve of, in this case, it's number of flowers, you can think of it as nectar or pollen availability. Warming climates in the last 45 years have caused this really dramatic shift in this curve. So seasonal time is seasonal patterns of availability are dramatically labile in response to climate change, and that is bound to have an effect on the trophic relation between pollinators and plants. Okay, then theory and experimentation. This is a hard question. I don't know how to answer it, but I think it is one of the richest theoretical questions we can ask. And that is, does spatiotemporally transient resource limitation produce net fitness effects? And really all I'm going to say on this right now is that this is basically the inverse of resource pulse theory. So there's been a lot of good theoretical work on how pulsed resources affect species coexistence and fitness. The idea there is that you have low resource availability, and then boom, you have like a mast year of a tree species, or you have the bloom of a mass flowering crop, and then it goes away. What we might have instead is generally high resource availability, and then these punctuated periods of shortage. So it's an upside down resource pulse, so to speak. And does that translate into net fitness, or do species recover from it? And here, I think one thing that will be critical is the ability of species to store resources like honeybees. I think that's basically the point of honeybee foraging behavior, is to buffer themselves against these kinds of shortages through nectar storage in the form of honey. Secondly, where there are fitness effects, are they stronger within or between species? This is the general condition of species coexistence. Competition is fine as long as it's stronger within species than between species. As long as that inequality holds, competing species will coexist. When it doesn't hold, they won't coexist. There are all kinds of ways this can play out. There's all kinds of complexity that can be introduced to the way this actually plays out. But at the end of the day, that inequality has to be satisfied. Intraspecific competition has to be higher than interspecific competition if competition exists and species are to coexist. Again, this is a hard question to answer. Then a question that I think is actually more experimentally tractable is we can test directly this hypothesized reciprocity between resource limitation for pollinators and pollen limitation for plants. So we can, I think, do flower bagging experiments to simultaneously track the depletion of floral resources by pollinators and the deposition of pollen grains on floral stigmata. And the prediction is that they are going to be negatively correlated, or they will be positively correlated, that resource limitation is going to be associated with saturating pollination services and vice versa. And this would actually be a pretty profound thing to be able to generalize. This would be really foundational in our understanding of the link between trophic ecology of flowers and florivores and pollination ecology. Okay, the conclusions, again, you've seen them before. I hope that the last 45 minutes made sense and that they're still somewhat fresh in your mind. So I hope that I've persuaded you that the trophic ecology of flowers and florivores is the foundation of pollination ecology, even though it has been systematically overlooked in the history of pollination ecology. Floral resource limitation, which is a precondition of competition, is contingent on floral resource structure. It cannot be assumed. We have to study floral resource structure if we are to understand limitation and therefore competition. The structure of floral resources consists of variation in time, space, and functional traits. This is hard to study. It's complicated. It all varies simultaneously, but I think it is worth it, and it is necessary if we are to produce a coherent picture of pollinator competition. I believe that these dimensions of floral resource variation are amenable to measurement, modeling, and ultimately integration with coexistence theory. This is not something that I expect to be done in 6 months. This is like, I could probably spend the rest of my career chipping away at this, and we'll see if that happens. In conclusion, I'll acknowledge Ingolf and Aaron, who I expect to be co-authors in this paper. This work really is sort of a recollection of Ingolf's early work on pollinator competition. And I think it picks up where he left off. And then a lot of this work was inspired by conversations with Aaron based on work that he did in New York State, looking at tracking pollen and nectar availability. And then I think the germ of this project goes back to a conversation I had with my PhD advisor, Reed, where he brought up the green world hypothesis in a conversation about resource limitation of honeybees, and that stuck in my mind, and I think it's kind of come to fruition in these thoughts now. I'll leave you with a picture of Philadelphia. It's beautiful, isn't it? And I think we have some time for questions.